Does quantum mechanics create time? In the last episode, we asked whether time really exists. We looked at diamonds, gold, light, and photons, and we asked whether time is a thing in itself or merely the way we describe change. That question now leads us into one of the strangest areas of modern physics, because if time is non-dimensional in the ordinary sense, then perhaps time is not something the universe was given at the beginning. Perhaps time is something the universe produces from something deeper. And one of the places physicists have looked for that deeper origin is quantum mechanics. Quantum mechanics is already strange enough without bringing time into it. It tells us that particles can behave like waves, that objects can exist in several possible states until measured, and that two particles can remain connected through entanglement, even when separated by great distances. Yet quantum mechanics also has a curious weakness. It uses time, but it does not really explain time. In ordinary quantum theory, time is treated rather like a background clock. The equations tell us how a quantum system changes with time, but time itself is simply assumed to be there already. It sits outside the system, quietly ticking away, as though the universe has provided a clock before the physics even begins. That is very different from Einstein's theory of general relativity. In general relativity, time is not a fixed background. Time is part of space-time, and space-time can bend, stretch, and change. Gravity affects time. Motion affects time. A clock near a massive object runs differently from a clock far away. A clock moving quickly runs differently from a clock at rest. So we have two great theories of physics, both enormously successful, but they treat time in completely different ways. Quantum mechanics normally assumes time is already there. General relativity says time is part of a dynamic universe. When physicists try to combine the two, the trouble begins. This is known as the problem of time. It is not simply a small technical difficulty. It is one of the deepest conflicts in modern physics. If the whole universe is a quantum system, then what outside clock is it supposed to evolve against? In a laboratory, we can measure a quantum particle changing with respect to a clock on the wall. But if we are trying to describe the entire universe, there is no clock outside it. There is no external observer standing beyond reality with a stopwatch. The universe must somehow contain its own time, or perhaps it must produce the appearance of time from within itself. This is where the Wheeler-DeWitt equation enters the story. We do not need the equation itself, but we do need the idea behind it. Wheeler and DeWitt were trying to combine quantum mechanics with Einstein's general relativity. They were looking for a way to describe the quantum state of the whole universe. But when they did this, something extraordinary happened. Time seemed to disappear. The equation appears to describe the universe as a single timeless whole. Nothing in it says, first this happens, then that happens. It is as if the entire universe is written down at once, not as a story unfolding page by page, but as one complete book already existing in its entirety. At first, that sounds impossible. We see change everywhere. Stars form, burn and die. Galaxies collide. People are born, grow older and disappear. Thoughts move through our minds. Clocks tick. The earth turns. The universe expands. How can any serious theory suggest that, at the deepest level, the universe might be timeless? Yet this is exactly the problem. It may be that time is not present in the deepest description of reality, but appears only when we look at smaller parts of that reality from inside. This is where quantum entanglement becomes important. Entanglement is one of the strangest and most powerful ideas in quantum mechanics. When two quantum systems are entangled, they cannot be fully described separately. They form one combined system, even if the parts are far apart. Measuring one part tells us something about the other. Entanglement is not just a connection through space. It is a relationship built into the quantum description itself. In the 1980s, Don Page and William Wootters proposed a remarkable idea. Perhaps the universe as a whole is timeless, but parts of the universe can still experience change relative to other parts. Imagine dividing the universe into two pieces. One piece acts as a clock. The other piece is the system being observed. The total universe may not change from some outside point of view because there is no outside time in which it could change. But from inside the universe, one part can be compared with another part, and this comparison creates the appearance of time passing. This is subtle, but extremely important. Page and Wootters were not simply saying that clocks measure time. They were suggesting that time itself may arise from correlations between quantum systems. If the clock part of the universe is in one state, the rest of the system appears one way. If the clock part is in another state, the rest of the system appears another way. To an observer inside the system, this looks like evolution. It looks like time passing. But from the outside, if such an outside view were possible, the whole combined quantum state may be static. This connects beautifully with the question we asked in the last episode. We wondered whether clocks really measure time or whether they merely compare change. Page and Wooters take this much deeper. They suggest that perhaps time is not something flowing behind events. Perhaps time is the relationship between one part of reality and another. In other words, time may not be fundamental. It may be relational. This does not mean quantum mechanics has solved time. It has not. The Page-Wooters idea is fascinating, but it is not the final answer. It shows how something that looks like time can emerge from a timeless quantum state, but it does not yet explain everything we experience as time. It does not fully explain the arrow of time. It does not fully explain why entropy increases. It does not fully explain why we remember the past but not the future. But it gives us a serious way to imagine how a universe without an external clock could still contain observers who experience time. This is where we must be careful. It would be too strong to say that quantum mechanics creates time in the same way that a factory creates a machine. A better way to say it is this. Quantum mechanics may show us how time can emerge from relationships inside a system that, as a whole, may not possess time in the ordinary sense. That is a very different idea from Newton's absolute time. Newton imagined time flowing independently in the background. Einstein made time part of space-time. Quantum gravity now raises the possibility that time may not be fundamental at all, but something that appears only when parts of the universe are compared with other parts. This also means that episode 30 does not contradict episode 29. In episode 29, we asked whether time really exists. In this episode, we are asking whether quantum mechanics might explain why time appears to exist. These are not separate questions, they are two sides of the same mystery. If time is not fundamental, then it must come from somewhere. It might come from change, it might come from entropy, it might come from memory, it might come from quantum entanglement, or perhaps all of these are different faces of the same deeper truth. So perhaps the question is not simply, does quantum mechanics create time? Perhaps the question is, can a timeless universe contain observers who experience time? And astonishingly, modern physics suggests that the answer may be yes.